Hello, everybody. My name is Dmitry Abakumov. I am the seminar chair today. I am very glad to welcome you all of you at the second international seminar on computational educational sciences. This seminar is aimed at building the research community and thinking together on challenging problems on the intersection of education, quantitative research, and computational science. Our seminar is co-hosted by the Center for Computational Educational Sciences of HSE University Moscow and the Open Lab for Psychometrics of Digital Learning. HSE University is one of Russia's top universities, a leader in Russian education, and one of the preeminent economics and social sciences universities in Eastern Europe and Eurasia. The Open Lab for Psychometrics of Digital Learning is a brand new lab, a non-profit lab, bringing together scholars and experts in psychometrics, machine learning, and educational sciences from HSE University, University of Colorado Boulder, University of Illinois Urbana-Champaign, Coursera, and Pearson to develop theoretically grounded, data-driven, explainable solutions to show when and why digital learning happens, to explain how digital learning products work, and to ensure that teaching solutions benefit digital learning around the world. Today is a special day because we are lucky to discuss a topic at the intersection of two intensively growing fields in educational sciences: learning analytics and virtual reality. I am cordially grateful to our speaker, Dr. Guillermo Santamaria Banfil, for his acceptance to present at our seminar. Guillermo works for the National Council for Science and Technology of Mexico. His areas of research and expertise are machine learning, data-driven problem solving, and nonlinear analysis. Currently, he's working on the development of ML and NLP methods for personalized instruction. So I'm excited, and I hope you are too. But before giving Guillermo our virtual microphone, I would like to inform all of you about the seminar plan today. So we will start with a 30-35 minutes presentation from Guillermo. Then we will have around 40-45 minutes for questions and discussion. One moment, I will admit a new participant. Okay, great. There are two options to ask questions. The first one, you can type the question in an open chat and I will voice it. And second, you can use the raise hand button and I will give you the virtual microphone. And a gentle, kind suggestion, if possible, of course, please use your web cameras on. Please use your web cameras on during the seminar to provide the kind of feeling of a real physical audience. Thank you for your understanding. Well, now please join me in warm welcoming Guillermo at our virtual stage. Guillermo, welcome.
Hi, good morning, everyone. Well, I will start presenting. I hope you can see it. Well, as Dimitri said, my name is Guillermo Santamaria Bonfil. I work for the National Council of Science and Technology from Mexico, and I was assigned to a project in the National Institute of Electricity and Clean Energies here in Mexico. For developing tools, educative tools for the power sector industry. So one of the products I have been developing is the analysis of a virtual reality training system used by this company. So the presentation which I'm presenting today, it's called Learning Analytics for Student Modeling Virtual Reality Training Systems. So this is the agenda. We will review the study case, which is virtual reality training systems for line workers. I will explain what a line worker is. The presentation will consist in a problem definition. I will explain the materials I used, the proposed model or methodology, our experimentations and conclusions. And finally, we'll have time for question and answers. So this is the work I'm presenting today, which was recently published in the Computers and Education Journal. And it's called, well, as the presentation. Problem description and proposal. Well, nowadays, in modern society, electricity plays a fundamental role. And this electricity is distributed using the power grid. Loosely speaking, the power grid consists in 4 elements, which are the generators, which produces the electricity, the transmission network, which distributes the electricity from generation to rural and urban zones. And then in these, once information or electricity is in these zones, it is again distributed by the distribution grid to the customers, which might be houses, enterprises, industries, etc. All this infrastructure from the transmission to the endpoint where the energy is delivered to customers is maintained by some guys which are called line workers. These line workers belong to the utilities staff, and they carry out lead line maintenance. This lead line maintenance consists in carrying out some procedures using tools and equipment in a lead line, which is a line which carry out electricity. This is for these operations are carried out on lead lines to maintain or guarantee some quality and to provide cost-efficient services. But this involves high risks, which might almost all accidents for line workers conduce to lethal consequences. So they try to avoid all of this, and to avoid all of this and to maintain a good quality on the service provided, they must ensure that the training received by these line workers is proper. So for this, they have developed virtual reality training systems, VRTS. And one of the main reasons for this is to provide contextualized environments. As I said, this maintenance is carried over lead lines, which are lines with electricity. So trainees, which lack of the proper training, cannot go to the field to practice over this type of infrastructure. So the virtual reality provides a real-world scenario with risk-free exploration and repetitive practice. Also, because this is in a virtual environment, it provides an increasing motivation and engagement to line workers. I must emphasize that what is learned in these virtual reality training systems are those maintenance procedures, maintenance maneuvers, or tasks, which I will use interchangeably across all these presentation. So they learn these procedures in which they must follow a sequence of steps, which involves also the use of tools and equipment to carry out some of these steps. However, most of the work that has been involved in the development of these systems is to improve the reality of the systems by integrating, for instance, augmented or mixed realities, as we can see from Cabral et al., which they developed a hot stick, which resembles the real-world scenario. However, the evaluation in the real world or in the field practice and in the virtual reality training systems depends on human instructors. It still depends on human instructors to define if a trainee is trained or untrained. So if we want to improve the educational processes, we need to guarantee the proficiency of trained workers using these virtual reality training systems by building a model which can relate the information that is recorded on these virtual reality systems, which might be student information such as age, last degree of education, etc. Could design elements like the time assigned for each maneuver, to learn each maneuver, how many maneuvers are taught in each course, etc. And trace data, which might be the record of sequences, like tasks visited, visited, which are maintenance maneuver visited, errors committed by trainees across the virtual reality training systems, mouse movements, etc. Although this is not a very new, well, it's not a new approach. For instance, we have seen that in the surgical skill evaluation in the medical sector, it has been used to compare the behavior of experts against novice using suturated robot-assisted arms. So, for instance, you can see on the upper of this image how the trajectory of these robots of these robotic arms that are manipulated by experts, and in the bottom you can see the manipulation of these arms by a novice. And in particular, you may see that the left hand in the case of novice is particularly noisy. So all these visual visual evidence needs to be put into a model that will discriminate between novice and expert. So the research question that we explored in this work was, can we discriminate with reasonable accuracy between trained and untrained workers with machine learning techniques using only record data from the serious virtual reality training system? The research question 2 was, can we identify the most important features and their impacts in their success or failure? And the research question 3 was, can we identify patterns that relate errors displayed by students in the virtual reality training system? And for all of this, we used several elements, which I will describe in the methodology. So the materials that I used that we use for this work, we analyzed a virtual reality training system that is called Allen 3D, that is used to taught maintenance maneuvers in the distribution grid, which I already explained which was. So this virtual reality system taught 43 maintenance maneuvers, and it consists of steps and sub-steps that you can see here in the interface of the virtual reality training system. So the student needs to interact with this interface in accordance to instructions, and which are these, and to the objectives of each step. By clicking on the interface or by selecting the proper tools which are displayed here. So the information that is recorded by this virtual reality training system is user information, which consists on the ID, on the user role, the geographic zone, which is located the job and the area, the number of courses he or she has taken, the maneuvers he or she has taken. Also, it also contains information regarding courses, like the course time, the number of maneuvers in each course, etc., the facilitators per course, the maintenance maneuvers per se, which are the steps and sub-steps that compose each of these maintenance maneuvers, evaluations, which are the human evaluation, which consists on exam grades, and trace data that is collected by this virtual reality system that consists in tool selection errors and maintenance maneuvers execution errors. So while they are elaborating, for instance, in this step where they need to click some security belt, which is shown here, they can commit several steps by clicking outside this area, or by selecting a tool which is not required, etc. So there are 7 types of errors that are recorded, but I will not detail them for now. The other, okay. So the other element that we use here is called learning analytics. Learning analytics is nothing else but a multidisciplinary area which involves machine learning, statistics, data mining, big data, natural language processing, and several other several other disciplines for the solution of educational problems. For instance, the prediction of performance, assessing sleeps, assessing misconceptions, giving feedback, etc. But what I think is most important of this area, the learning analytics, is the process followed to develop the model. So we start with a real world problem in which we have data, in which we don't even have a hypothesis about regarding what we're solving. Then we start collecting raw data and processing it and cleaning it. From this process, we obtain all these, some hypotheses that we can solve from the observed data. This also depends on the data scientist, on the expertise of the data scientist, and all the stakeholders involved in this process. Once data is processed and cleaned, we carry out an exploratory data analysis, which is visualization of this data. And we carry on also modeling with machine learning models. For instance, in this case that we want to discriminate from trained and untrained students, we use all the observed data in the virtual reality training system to try to build a model that can predict from this observed data if the line worker is trained or not for a specific maintenance task. Once we have explored the data and built this model, it is validated through a statistical analysis, which is statistical analysis, which is a standard. And then you also analyze this information with the stakeholders, which in this case are the people involved in the training of line workers. So to validate that the models or the insights that we are obtaining are useful. If these insights doesn't seem really useful or use information that will not be available during the evaluation, for instance, if we cannot have the age or the sex or the job role, etc., during the evaluation, the model cannot be used. So if the model cannot be used, then the process is repeated, which is an iterative process. And if the model is useful for the stakeholders, then it comes to a data product. No? So they can, for instance, in the case of the utility or the people who are using this virtual reality training system, they can incorporate this model so they can use it in their training process. Now I will explain our methodology, which can be summarized in this graphic. First, we take the Allen 3D database and we granulate it because it has, since we part from the problem. So the problem is that this virtual reality training system wasn't developed with the thought in the mind that it will eventually promote some self-evaluation or has an automatic evaluation of each task. So the building of the tool of the virtual reality training system doesn't match our needs in terms of machine learning. So we have to granule the databases. Once the database is suitable for our analysis, this is a table. We select a case of study. We transform the information from in some variables which are categorical. We need to transform them to numerical for some of our algorithms. Then we map trace data to a bag of errors, which is, it's inspiring an idea of the natural language processing or text mining, which is called bag of words. And then we incorporate the additional information that the virtual reality training system stores, which is course and training's additional features. Then in parallel, we run an exploratory data analysis using a choreogram to try to cluster error sequences in a heat map, if you want to see it like that, or a correlation matrix. And also, then we build a machine learning model. Well, we test several machine learning classifiers, which I will explain in a further slide. Then from the winner classifier, we perform a feature selection And we assess also the performance and class imbalance. Or these two characteristics, in particular class imbalance, which we will discuss later, hits or affects directly to this ML classifier. So we need to address this class imbalance. And once we have all our ML classifiers, we test them all. We choose the best, which we will explain which is the best. And over this best ML classifier, we carry on a feature importance analysis to determine which are the most important features that are affecting that a trainee is trained or untrained after evaluation. Once altogether, this form our student model, which is analyzed using statistical tools, and also by the stakeholders, which I already said. Well, the case of study consists in 8 years of data from approximately 1,400 students, from 329 courses, 43 in which were 43 maintenance maneuvers taught, and the database recorded 4,800 students' evaluations, which is composed also from 104,000 errors, from which almost all errors come from the execution of the procedure. And well, 14,000 of these errors comes from the tool selection. So as you may see, almost all errors are concentrated in the execution of the maneuver, in the execution of these steps. However, as you may see in this graphic, from the 43 maneuvers, only 5 have enough information to build a classifier. This is only the maneuver 1, the maneuver 16, maneuver 17, maneuver 36, and maneuver 43, which I'm avoiding the name, of course, have enough information for building a model. So we pick only these maneuvers to build a classifier. Then, well, for each maneuver, we record errors, as you may see here. We have the ID of the trainee, the maintenance maneuver ID, the number of steps in which the error was committed, the sub-step, and the error ID. As I said, there are 7 types of errors, so the types are here, and the steps and sub-steps from each maintenance is recorded here. This sequence of errors can be mapped, as I said, using an idea from text mining, which is called bag of errors. Since we are analyzing a sequence of errors, we would like that each error in each step or sub-step corresponds to a word. So we map, for instance, this error as a word that is, is encoded like this. Step 5, sub-step 1, error type 1. This is the encoding. So, as you may see, from a maintenance maneuver, you may have several types of errors with different frequencies, which is summarized in a bag of errors matrix, which is shown here. So for each row, we have the students, and for each column, we have these errors, right? And so in each cell of this matrix, we have the frequencies of the errors. Okay, so, well, we already have our bag of errors, and we now want our dependent variable, which is if the students are trained or untrained. We managed this approach because the instructor evaluation ranges from 0 to 100, but unfortunately, we don't have the lowest proficiency score. In fact, the evaluation of a trainee is carried out by several instructors within some sort of of ensemble or voting scheme, they decide if the trainee is trained or not. So they only give you, it doesn't matter if they got 80 or 90 or 95. It depends on the errors they commit, that if they are allowed to be considered trained or not. So instead, instead of using this scale for dependent variable, we use a binary variable using several thresholds, as you may see here. We use as a lower proficiency score 80, 85, and 90, and this induced in the different maneuvers several populations of the trained and untrained students. So for instance, for the lower proficiency of 80, for maintenance maneuver 1, we have that 30% of the data is untrained and 87 of the students in the data are trained. From our maneuver 16, only 5% are untrained, and so on. So as you may see, even when we use 90 as our lower proficiency score, there is a high imbalance between classes. So we need to address this. Well, the other information that we include in our model is this feature that is, it's a vector XORDER, which contains the information from the job zone, the job area, the number of maneuvers he she has taken, etc., for each student. However, some of these, such as the job area or the job zone, are categorical features, which, for instance, some of our classifiers, such as support vector machines, logistic regression, or canny-red neighbors, doesn't support categorical features, well, at least not in their classical form. So in order to use these variables in these algorithms, we have to transform these variables from categorical to numerical. And for this, we use the weight of evidence, which is a simple formula, which is the logarithm, the natural logarithm of the event over 1 minus the event, the probability of the event. So in this sense, we can transform our data from categories to numerical features. Also, well, then once we have all the data properly manipulated, we carry on 2 steps. One is the machine learning modeling, the other is the exploratory data analysis. For the exploratory data analysis, we use choreograms, which is a clustering of the correlation metrics. For instance, you see here a correlation matrix in which you have, well, the errors. Here is step 1, error type 4, step 7, error type 1, etc. So you have all these errors, and you want to cluster them in accordance to their correlation. Perhaps you may think of using, for instance, k-means or hierarchical clustering. But a disadvantage of this type of methods is that although you can have clusters of similar elements or correlated elements, you cannot order you cannot have an order intra-cluster within the intra-cluster. For instance, these two, step 2, error 4, and step 17, error 4, have a very high correlation, as you may see by the color encoding, which goes white, which has no correlation, very blue or dark blue for high correlation, positive correlation, and dark red for negative correlation. As you see, there is no negative correlation between errors, only positive correlations are appearing. And so for clustering these and to give intra-clustering and extra-clustering ordering of the elements, we use choreograms, which is nothing than ordering each feature of this matrix by the angle of each point projected in a biplot. So for instance, these features that are grouped here, which you could see like points instead of arrows, are grouped within this cluster. And also you can see that the angles between these these errors is very short. So this is the interclustering ordering that is induced by this core graph. So for building our machine learning model, we follow this procedure. We take the data, we separate in K holdout sets, which are training and testing sets. So we want to repeat this experimental setup 5 times. So we train and test with different subsets 5 times to have a better approach of the error of our models in the testing sets. So first we divide it, we create these divisions or these subsets. Then we carry on a feature selection, which for the categorical data was biserial correlation, and for the rest was correlation. However, this feature selection is very naive, if you want to think of it. And also, some of our machine learning algorithms, such as the decision tree or the random forest, don't require this feature selection to their formulation. They already carry out their procedure for feature selecting, so they don't require this feature selection to be carried out. So after we carry out the feature selection for the selected algorithms, we perform a K-cross validation, which is estimating the parameters of the model. And then once we estimate the parameters of the models, we carry on our testing performance using these metrics, which is the true positive rate, the false negative rate, true negative rate, the balance accuracy, which is the true positive rate plus true negative rate over 2. This is used that we have a very imbalanced data set. So we need proper measures that can assess the quality of our models using imbalanced data. Also, we use the area under the curve of the raw curves or receiver operating curves. Receiving operating, well, I don't recall what the acronym means. Well, but we use also the area under the cube rock and area under the cube precision recall curves. And these are the parameters that we use for these algorithms. Finally, using the best algorithm, which we will come later, we carry out the feature importance analysis. That is, over the testing of these models, we define several important features for each set. So in the end, we have to summarize all these features. For instance, you got that feature 1, 3, and 5 are important. For instance, in this subset, you find that 1, 10, and 20 are important. So they need to be summarized. So we use a simple mean for the importance of these features. And through this, we assess the importance of each feature. Now the results. Well, for the research question 1, can we discriminate with reasonable accuracy between trained and untrained workers with machine learning techniques using only record data from a series virtual reality training systems? Well, here are the box plot for all measures, for all our algorithms test for the 5 proficiency threshold. So here we didn't consider the thresholds. We only used the results for classification using the lower proficiency of 80, of 85, and 90 for the decision tree, for the accuracy measure, balance accuracy, and also for the area under the cube of the precision recall curve, and so on. No? So as you can appreciate from this figure, random forest is one of the most accurate algorithms, although you can see that the true positive rate is trivially high. This is due to the high class imbalance. So this measure is ruled from the rest of our analysis, since its result is trivial. And considering all of these, all of the results for each of the algorithms, we carry on a weight test to compare all algorithms and to define which of these was better. We use a weight post hoc analysis, so we can compare in pairs which algorithm has a significant difference over the other. For instance, Candidate's neighbor has a significant difference over the decision tree. Random forest also has a significant difference over the decision tree, and so on. No? From this, we reduce our scope of the possible algorithms, and we analyzed the proficiency scores. Analyzing the proficiency score, we can see that by increasing the proficiency score, we have a better discrimination of untrained and untrained students, even though this is expected, no? But even though this is expected, well, this was like a requirement of the stakeholders that this classification, or that this increase in accuracy by increasing the proficiency score is maintained. So as you can see, for all algorithms, this is maintained. Then we carry out the same analysis for determining which algorithm was the best. And to summarize it, we found that the random forest, which can be seen in particularly here for the highest proficiency score, has the better discrimination between trained and untrained students. However, as I said at the beginning of this presentation, what is most important for the utilities personnel is to identify those untrained students, because these untrained students go outside the field practice and go to real world scenarios where they can get injured. They can be seriously injured. So we need to detect, to focus on those algorithms that excel in the identification of untrained students. So as you can see here, the maintenance maneuver 1 is the one where it's more feasible to identify those untrained students. However, unfortunately, by overfitting to the untrained student, as you may see here. Here I'm showing only two metrics, the true negative rate and the area under the curve, precision recall curve. So as you can see, here we have more identification. Almost 80% of the untrained students are detected by overfitting to these untrained students. Nevertheless, when we discuss this with the personnel, with the utilities personnel, which are in charge of the instruction, they think this is desirable. This is desirable for the system. Also, we can see that for the rest of the maneuver 16, 17, and 36, we have a low detection of the true negative rates. This is also a consequence of the high imbalance of the classes. And for maneuver 43, we also see that for maneuver 43, we see that there is a better separation between trained and untrained students. But we also assume that this separation is due to the high imbalance in classes. Let me rephrase this. The maneuver 43 is the most balanced maneuver from the tested or from the case study. So we can see that this behavior, it behaves better in terms of the area under the curve of the precision recall curve, and also the true negative rates in general. See, because here random forest is good, but the rest of the algorithms perform really bad. Unlike for maneuver 43, where all maneuvers perform, well, not that good, but not that bad as maneuver 1, and in general, they induce a better separation between classes. So we decide to carry out a feature important analysis over the random forest due to this analysis. And we want to identify the most important features and their impact on determining student success failure in specific tasks. So for instance, here are all the features, or well, not all the features, but a subset of the most important features sorted by its importance for the three proficiency thresholds that we use. So in color yellow, we see the 80 proficiency. For teal, we see 85, and for purple, we see 90. So a thing we can observe is that the area where they come, the area from where students come, is the most important feature affecting that if they are trained or not after the evaluation. Also, the total course of time affects really well, has a high importance for determining if a student is trained or not. The zone, the number of maneuvers taught in each course, and then we have some information regarding the trace data that is recorded. This is the errors committed in each of these. I also have to say that this analysis is carried over only over maneuver 1 due to this, no? Because here we identify the most untrained students, and we want to identify why. So these are self-explanatory, and I will not discuss, but these trace data or these trace errors are shown in these figures. For instance, these are step, this is a step 4, I think, C and D, yeah. This is step 5, can you see my pointer? This is step 5, and this is step 4. This is our consecutive steps, and in the red box is highlighted the area where the students are required to click. So this maneuver is for rescuing an injured line worker. So, for instance, during a maintenance maneuver, a line worker may suffer an electrical shock. So, line workers need to know which are the proper process to bring the injured line worker down and to give them the proper first aid. So these are the elements we found that are most crucial in detecting if they are trained or not. And also these tools are highly selected in this maneuver, which, well, these are selected even while these are not required, these tools. When validating this with the stakeholders, we found that since these tools are not required in this maneuver, one of the reasons students might be selecting this is because they are carrying out some actions that they must carry out in all processes. For instance, when they arrive to a site where they are going to work, they need to use these cones to delimit the zone. But for instance, in this maneuver, they are already carrying out a maintenance maneuver, so they have already selected the cones and they have delimited the zone. So these are not required in the maneuver. Still, students are selecting this type of tools, and the reason we found it was because they might be confused regarding the steps they must follow. We might even want to assess further the impact of each feature regarding the discrimination. So, for instance, we took the variable zone, which has 8 possible zones. This means that each student belongs to one of these zones, and we have the weight of evidence, the value of each weight of evidence. This is the zone transformed from categorical to a numerical value. An important aspect of the weight of evidence it gives us an idea of how good this value is for discriminating between trained or untrained students. So for instance, the zone 2, zone 5, and zone 8 is good for discriminating students that are trained, and zone 7 and zone 10 are good for discriminating students that come or students that will not be that will be untrained after the training. Finally, the research question 3, that is that we can identify patterns that will obey the underlying relationships between errors displayed by the students' trace data. We build these programs, that is the correlation matrix sorted by the two principal components, or by projecting into a big plot all points, and by finding or by sorting these points in accordance to the angle between points projected in the biplot, or these loadings. So here is the results for maneuver 1. This is the errors for the maneuver execution. These are the errors for tool selection. As you can see, in the case for the maneuver execution, correlation between errors is really low. There is only high relationship between some steps, which is step 1, step 2, and step 11. But it might be a fluke. This is really difficult to address. But in the case of the tool selection, we can see that there is a high correlation. Even we have a correlation of 1, meaning that all these features happen with the same frequency almost all the time, or all the time. So if we zoom to this part of the program, we can see which are these tools, and we can see some things. First, some of these tools are very similar. Some, for instance, look at this range, which are only different in the sizes, or in this, well, in Spanish are called dedales. I don't say how to say in English, but they are very similar, and they are only different in the size of the, I don't recall the word for tornillo, but, well, these are only different in sizes, but they are the same, as you can see. Nevertheless, even while these are very similar, they are not even required for this maneuver. So when we present this result to the stakeholders, it was useful for understanding this, because we can see that all these tools are not required in the maneuver, and so the students might be confused about the maneuver, or might be thinking, or might be guessing, but guessing will lead in a lower correlation. So since this is a very high correlation, almost of 1, we can see that the students might be confused about the maneuver they are solving. So for our conclusions, we have, for our research question was that increasing strictness increasing the strictness of the evaluation raises the discriminatory power of our ML algorithms. Students' performance for lower proficiency thresholds were better characterized by local approximations. Well, as you can see here, here in the table, for instance, can nearest neighbor, in comparison with random forest, it's not really, the results are not really different. So this can also be observed, for instance, in the support vector machines. Due to the assumptions of these two algorithms, we conclude that the students' performance for lower proficiency thresholds were better characterized by local approximations, which are these candidate neighbors, whereas higher maximum scores were characterized by more general reasons. Also, we have that class imbalance led to overfitting to machine learning algorithms, which in fact is not a desirable thing, but is useful for the purpose of the utilities. For our research question two, we were able to identify the most important features for discrimination and their proportions in such contributions. In particular, we found that the weight of evidence allowed to explore further the discrimination power of each feature. This type of analysis allows to pose if-else rules. For instance, in the case of zones and areas, as we saw in the weight of evidence graphic, we can think of if-else rules that apply to people that comes from zones that have a low proficiency or who obtain a low proficiency rate for, I don't know, well, when we validate this with the stakeholders, what we found is that these zones were, in fact, remoter zones. These zones have the worst availability of internet and the worst availability of electricity. So this has a huge impact during the practice of line workers. So as I'm saying, this can be translated to if-else rules. So if these guys come from these zones, you can relocate for the evaluation or relocate for the training to the nearest zones, or perhaps to train during times where the electricity has lesser probability of failure. And for the research question 3, we saw that the programs are useful in revealing patterns of correlated variables errors, whose linear, and I put it here in between parentheses, because the analysis, the sorting of the program is induced by projecting the loadings of each feature on the eigenvectors. So our assumption is that there is a linear relationship, and whose covariance is well explained by their two principal components, which is the big plot. And this tool is also useful for constructing bulk libraries, because, as I said in this slide, we can focus on this particular triangle of highly correlated features to give feedback during the evaluation or during the practice to the student. Well, there's limitation, of course, in this approach. Given its accuracy, for the time being, these models cannot replace traditional examination, because we would like to identify at least 80% of the untrained students, which was only possible in one of the maneuvers. So we cannot replace traditional examination by human instructors, but we can provide a tool that can be used also during traditional examination. Model is focused on a particular knowledge domain, which is high-risk training electricity, and to a particular geographical zone. So this analysis models only the requirements of this particular geographical zone or individuals. There is a high class imbalances that lead to a low in trained students identification. The model, although can be used to assess knowledge components feedback, still depends on human structures. And automated feedback can be articulated with a formal knowledge model. For instance, although all the information is concentrated in the virtual reality training system, the relationships between the steps is only in the mind of the structures. So, although there is information, right? There is manuals, there is books, and another type of text document, but there is not an ontology or a map that can map these steps. So automatic feedback can be articulated with a formal knowledge model. And in terms of the BOE, in terms of the bag of errors, we can use models or more advanced natural language processing. because bug of errors, some of its limitations is that it only focuses on the frequencies of words and not on the sequences. So if sequences, as we've seen in the program, are meaningful, the bug of error will not be able to map it. And finally, more data is required. And that's all. I hope I was in time. It's time for questions and answers. Thank you.
Perfect, Guillermo. Thank you very much for very interesting presentation. Yes, we still have time for questions. And who will start? Who has the questions? Okay, we have a first question. One moment, and I will voice it. Okay, Natalia is asking, Guillermo, thank you very much for the necessary and very important information from the world of learning analytics and virtual reality. Currently, research is also considering the physical capabilities of a person when studying in virtual reality. Perhaps you plan to use research in this area in the future. Students' failure in training can be a result not only of their social status and level of education or learning conditions, for instance, lack of internet, electricity, or didactic errors in the process of obtaining the most important knowledge components, but also as a result of physiological features of content perception through virtual reality training systems. For example, problems with students' vision. Can the proposed student model based on learning analytics in the future take into account the physical characteristics of students as one of the variables in this model, or when establishing cause and effect relationships between their most common errors? So this is the question.
Okay, yes. Well, currently, as you have seen, the virtual reality training system is very limited. In fact, that's a requirement of the utility because they want the cheapest tool, which can be disseminated across all their facilities. So they require that only a mouse, a computer, and a keyboard is required. So the system per se doesn't capture information such as your emotional states, or doesn't capture additional information, which also could be useful, like as you said, social status information, which I think it might be a really useful feature. Let me read back your question. Can the proposed student model based on learning analytics in the future take into account the physical characteristics of the students? Well, I'm not sure if all type of people are allowed to be line workers. As you see, they need to climb poles, electrical poles. So they must have, I think, two hands, to feet, to legs. They must have some physical requirements, and this could be and a utilities discrimination factor, which only focuses on people who can be have the proper training and who can carry out the processes. So I don't think physical characteristics of students such as this can be included. However, other physical characteristics may be included, such as the weight, height, etc. I don't think. I don't know. I don't know if this will have any impact on the analysis. This information, in fact, is not recorded by the utility in other systems, which we want to use, but this type of information is not used. I don't think. I don't know if this is because of to avoid problems with discrimination, or I don't know. But You may think that this can be useful, but I'm not sure, to be honest.
Okay, thank you very much. Questions? More questions? Yes. One more question from Daria. Thank you very much for the presentation and interesting report. For what other specialties, except linear workers, virtual reality technologies can be useful? Do you plan to use another sample for the research?
Of course. Yeah, there are many types of virtual reality training systems for high risk activities. For instance, there is the CANARM system, which is for training astronauts. There is also a virtual reality, well, for the medical sector. Although there is not, for the medic, there is not a high risk situation or probability. For the people who are being treated, there is. So, for instance, in the case of the surgical skills, which I presented earlier, let me share. Okay. So you see my presentation, right? So, for instance, in this case, you may not think of the tools, but you can think of movements that are wrong. So this sequence can be split into subsequences. So perhaps some sequences like these elements here are correct, are well elaborated by the novice, but the movements which are, I will try to present larger so you can see it better. So, for instance, these movements here are correct in the novice medic, but these movements here are not. They are I don't know, becoming intertwined, or it can hurt the patient. So you can break all these trajectory into subsequences and analyze it. Instead of analyzing tools, you can analyze subsequences. Did I answer your question?
Yes, I think. Thank you very much. So Irina has the next question. Thank you very much for the presentation. Do you consider the opportunity of ensembling 2 or more algorithms to improve or boost final algorithm's performance? And I also have not the same question, but in the same direction. So like your work covers several methods of statistical or machine learning. So we know that some methods are better in terms of flexibility and prediction, while some methods are better in terms of interpretability. And also we know this phrase that there is no free lunch in statistics and machine learning. So according to your data and your experience, which method would be the best balanced choice in terms of both flexibility and interpretability? I think that so my question is about one method, and Irina's question is about combination of algorithms.
Okay. Well, you can think in a combination of algorithms. You can think in an ensemble. And even while there are algorithms that doesn't carry out a feature importance analysis. For instance, in the logistic regression, you have the marginal effects which can be obtained from the weights of each of the features. And in the random forest, we also have the decrease in the impurity of each node. But even, for instance, in the case of k-nearest neighbors or support vector machines that doesn't induce feature selection, we can pose an step like we did for selecting these features, and by carrying a statistical analysis, we can detect these features. I'm not sure which will be the best algorithm to use, but I'm sure of this. It depends on the data available. So, for instance, in this case that we have approximately 100,000 data points that was reduced because we didn't use all that data. We only used those that pertain to specific tasks. So the data is considered medium or small data. In this type of settings, machine learning works well. You don't need to use deep learning or perhaps ensembles. You only need to properly tune the parameters of your algorithm. But once you have big data, once you're having more than a million of data points, you can start thinking about deep learning or these types of techniques that can improve or can exploit all of these data. Perhaps this comparison was not fair because we compare an ensemble model against single machine learning. This is random forest against support vector machines, logistic regression, candidate neighbors, and decision trees. So in this case, the ensemble model achieved a better performance. So in my next experiments, I will go for gradient boosting or this type of models due to the fact that I don't have a lot of data. But if I analyze another, or if you're analyzing other type of data, for instance, mock data that can give you really big data sets, you can apply other types of machine learning techniques.
Okay, thank you very much. So we have lots of questions. So Ekaterina is asking, Guillermo, thank you very much for your presentation. What do you think? How the problem of highly unbalanced data might be solved?
Okay, well, there are a lot of ways you can handle. Here, for instance, for the random forest, we use a stratified approach in which we guarantee that the same amount of trained and untrained students are selected for each tree. That's one approach, a simple approach. But you can use better approaches such as SMOTE or other type of techniques that can produce simulated data to artificially balance the data set. So there are a lot of approaches. Those are two. These two are, well,
yeah,
are the ones I suggest.
Yeah, thank you very much. Okay, yeah, Evgeny is asking, did you try visualizing decision tree as a graph with nodes with separation rules and leaves with information? Okay. Did you try visualizing decision tree as a graph with nodes with separation rules and leaves with information about purity of a given group? If yes, were these separation rules interpretable? For example, those who use tool X in a wrong way are likely trained and others are not.
Yeah. In fact, we already tried that in a conference work, but the accuracy of the decision tree is really low. So we didn't want to use a decision tree due to its low precision or accuracy or separation, the induced separation between trained and untrained classes. Yes, you can produce rules from a decision tree, but you can also produce rules from a random forest. So this is a good thing that of the random forest, that you can produce these rules to identify those that are trained, those students that are trained, and those students that are untrained, which can be readily interpreted by an instructor.
Mm-hmm. Thank you very much. Okay, so yeah, Vladimir is asking, article stated that it would be interesting to track mouse movements during VRTS usage. Do you have ideas what and why this could be useful? So Vladimir is working with eye tracking, and he knows about proficient novice studies in this field, but he is curious about motivation for mouse tracking usage. What kind of consecutive errors did you... so it was the first question. Let's start with the first question.
Okay. So what kind of consecutive errors did you observe during the learning process, excepting confusing similar tools? Well, we observed that there might be guessing. There is a lot of guessing in this type of tools due to the elaboration of the tool. Because in the tool, you only in the virtual reality training system, you need to follow the steps, which you can memorize without internalizing the content, or you might guess as you may see. But during the evaluation, you do not observe this type of behavior. So what we found most is that students, in fact, carry out a lot of have a lot of sequences of error that are from confusing situations. So, in fact, for instance, in the case of this triangle, since they are highly correlated, we can induce that directly. But well, and this behavior is not only observed here, but also here, here, and in a lot of elements. So, well, this is on those that we decide to focus rather than focus on, for instance, this type of behavior, which might be described by other type of I don't know, misconceptions or missing conceptions or sleeps. I don't know. So, in fact, we only focus on this type of analysis, and they belong to confusing similar. Well, not confusing similar tools, but confusing the tools that are required for a particular task.
Okay, thank you. It's also a question from Vladimir. So he's asking, what kind of consecutive errors did you observe during the learning process, except confusing similar tools?
I was answering that question.
Huh?
I was answering that question.
Sorry. Wow. Yeah. Okay. Because I just had to reply someone in the chat, and probably I just missed this response.
Yeah,
so
the following is learning analytics really so useful? I think it is.
Okay.
Well, learning analytics is just like educational data mining, or you can rebrand it with another name. What I think is the most important element of the learning analytics is this approach, which is an approach rooted in the industry. This type of model is followed by the industry. In fact, the model which I show you is from a book. I don't recall the name of the authors, but the name of the book is Doing Data Science, and it comes from the front line, from experts in the front line. So this approach is rather used in the industry, but here for scientific questioning, it is also useful, as you have seen, because although in my case, I'm not an expert in line workers training, right? I'm an expert in machine learning and algorithms. So many of the details behind the line worker training are obscure to me, but I found several important features such as the remote zones, the classification, which achieves a high level. So this type of approach could be useful when you start from a problem and from a system, rather than from a more theoretical perspective.
Okay, thank you. So Carlos is asking, Guillermo, thank you very much for your presentation and such an interesting topic. My question consists of 3 parts. First, for you, what is the difference between educational data mining and learning analytics? Second, have you ever considered the use of artificial neural networks instead of more classic machine learning algorithms? And 3, how did you deal with the overfitting issue, which is quite common in machine learning techniques?
Yeah, well, for me, as I said, there is not a clear difference between the 2 areas. For me, the main difference is the process in which the the research is carried out, as I presented. Whereas data mining, educational data mining, is more like in the straightforward, where you part from a hypothesis, from an observation, you pose a hypothesis. Well, the traditional scientific method. So this is the first question.
The second was, have you ever considered the use of artificial neural networks instead of the more classic machine learning algorithms?
Okay, yes. And for the third question, well, as you said, the overfitting. Well, in the case of the decision tree, for all machine learning, for all the tested machine learning algorithms, we carried a tune processing using a cross-validation process. So this is carried out to avoid overfitting. For instance, in the case of the decision tree, we carried out a pruning process. In fact, this is related to a question that was asked before. That is the type of rules that we obtained from a decision tree was, if it comes from these zones and it comes from these areas, if it comes from these zones and these areas, they are trained and non-trained. So the rules that we obtained from the prune decision tree were useless in terms of information that we can obtain. For instance, in the case of candidates neighbors, we also carry out a tuning of the number of near neighbors that were used. These are described here. So, for instance, the K-cross validation use a value of 5 sets. The K-holdout use a value of 5. For the candidate neighbor, we tested from 2 to 20 neighbors, and we selected the best. From the decision tree, we also test several parameters, and then we carry out the pruning. In the case of the random forest, it is you can control how large the tree grows, but it's not desirable. In fact, you want weak learners. So here we did not control for the overfitting. For the support vector machines, well, a good thing that has support vector machines is that it can handle pretty good the overfitting only by tuning these parameters. So we use, for instance, a radial kernel. We use a penalizing term, which was from 3 to 10, and etc. We use several parameters, and then we tune it through the K-cross validation. So that's how we handle overfitting. And we could use neural networks, of course. It will only require to plug and play another type of model and perhaps to tune it. But for the time being, I thought that 5 machine learnings and all this analysis was too. It was a lot to contain in the article, so we try to restrain our scope to not make that too big our product.
Okay, so thank you. Anastasia is asking, thank you very much for the presentation. It may have been discussed, but have you considered an overall number of errors as a feature? Also, I would like to clarify if there is any relationships between error types and tasks themselves over the need to use a tool. For example, the overall complexity of the task.
Well, we did not consider the overall number of errors as a feature. No, that's not true. In an earlier work, they consider the overall number of errors as a feature for each type of feature. But the performance of the model was not good. Also, the model is not good for assessing particular knowledge components. For instance, you have to review step 1, 3, and 5 because they share in common this element. Using only the overall number of errors, we cannot assess that, and that was a requirement. Also, to clarify if there are a relationship between error types and tasks, no, there are 7 types of error which can be committed in all maintenance maneuvers or all tasks. These are, I will. Here are shown. For instance, in the case for tool selection errors, the errors recorded are unnecessary tool selected, incorrect number of tools, and selection of an already selected tool. These are the errors that can be produced. And for the execution error, these are wrong element select in the environment, unnecessary tool selected, element selected when a menu action is required, a tool selected when an environment interaction is required. So these all apply to every task, all the tasks that are contained here. And the complexity, we are trying to calculate the complexity using entropy-based measures, but this is an undergoing work, so we have not already considered this complexity, although there are several ways in you can measure complexity. We are thinking in a statistical approach of the distribution of the errors across each case. But as I said, this is an undergoing work.
Thank you. And we have the last question in the chat from Stanislav. He's asking, Guillermo, did you use IoT sensors to collect historical data for your machine learning models? TinCan standard to collect data about students' performance using VR. So it is the last question in the chat. So you can read it because probably okay.
Yes. I'm trying to follow with all questions. Before I answer that, I'm answering an answer that asks about the mouse tracking. Mouse tracking, it might be a good idea because it track the mouse or the mouse movement. It might be a good idea because we can estimate if a student is focused on the task or is thinking in something else, or he is perhaps guessing or exploring. We can characterize their behaviors using perhaps a clustering approach. Nevertheless, this tool doesn't track this information. So although it will be desirable, this tool doesn't track it. And regarding the question of Stanislav, we do not use IoT sensors, but the project is considering this. Well, not perhaps IoT, but to include more sensors. For instance, a camera that can detect facial expressions, that can track gaze. Also, we are working with a chatbot with the Alexa framework. And although these types of systems and Unity per se does not have does not have a plugin for ThinCan, for the X API, you can translate all of these actions into learning statements or learning activities using the standard and then report it. In fact, we have already been explored that, but using only a navigator, a web navigator, using a bookmarklet. But it will be also useful to include that type of information in the virtual reality training system.
Yes, I have unmuted myself. Thank you very much, Guillermo. I think that it was great presentation, very interesting, and the evidence for it was the wide variance of questions on different points of virtual reality, machine learning, statistics, and so on. So that is why, thank you very much. We are very happy to have you today here. So I have my final remarks. So our next seminar the third seminar will take place on Thursday, September 3rd, at the same time as today. So we have Diego Olaya from Free University of Brussels, Belgium, and he will make a presentation on uplift modeling for preventing student dropout in higher education. So you are very and kindly invited. So next week, I will send you an announcement to make you suitable to set up your agenda before summer vacation. And now I just would like to ask everyone to unmute your microphones and to join me in applauding Guillermo and thanking him for today's presentation.
Thank you very much.
Thank you very much, Guillermo. Thank you, everybody, for joining us today. And I hope to see you at our next seminars. Have a nice rest of week and have a nice weekend.